Alright, class. Today we are going to talk about the topic 7.10 reversible steady workflow. So, 7.10 reversible steady flow work. Let me give you the little bit background of reversible and steady flow work. So in previous classes and also in previous chapters we determine the work done by a thermodynamic system when it goes through quasi-static equilibrium, and also we determine that work done for a closed system, right? So if you have a closed system like this, and it can change the volume, right, and it can change the pressure. So if this is a closed system, for this type of closed system we determine the work done by this type of closed system, right? W equals to 1 to 2 and P times dV. We determine the workflow for this type of closed system. However, let's take a look. What if the system is open system and the flow in the system and flow out, flow to the system and flow from the system is steady, right? That means that if you have a, for example, a turbine, right? If you have a turbine, then in that turbine, the flow is incoming flow and outgoing flow is steady, and that turbine is producing some work, right? W. Right. So if we consider this type of system, then what is the work done, right? So if this is a reversible system, reversible system, as well as it's a steady flow, right? Reversible and steady flow system. So what is the work done or work produced or work consumed by this type of device, right? So this is input and this is output. Okay, so let's derive the relationship for this system, right? Let me choose. So for quasi-static equilibrium process, or for closed system, we know that excuse me, area under the PV diagram, area under the curve of the PV diagram, it represents the work, right? So that relationship is equals to P times dV. But for the reversible and steady flow system, the work produced by this type of system, we, since it's energy is coming, energy is leaving the system, that means that we have to use the conservation of mass, our first law of thermodynamics, right? So if we write the conservation of mass, not conservation of mass, it will be conservation of energy, right? Energy, or first law of thermodynamics, then it will be delta Q reversible minus delta W reversible equals to dS. I'm writing it in terms of enthalpy of that working fluid, right? Plus dKE, excuse me, dKE plus dPE, right? That means that net energy balance of that equation is the change in internal energy, change in potential energy, and change of enthalpy. So for reversible process, the heat transfer, we in the previous class we found that delta Q reversible process, we found that the relation between the heat transfer and the entropy is equals to T ds, and also the TDS entropy and the enthalpy relationship was TdS minus VdP, right? We have this relationship. If you look at the book or the previous class, we derived this equation, or we deduce this equation for 7.16, and we had this equation 7.24, right? So now if we plug in these values of q reversible and dh, then we can simplify we can get the term in terms of equation in terms of the w revolution, or the work done w reversible, or the work done by the system, right? So that would be minus w reversible delta w reversible equals to v dp plus dke, actually this dke plus dpe, right? So this equation is so if we simplify, or then this equation will be, if we take the integration of this system, right, for the process 1 to 2, then the work done, reversible work done, would be w reversible work done would be integration of negative 1 to 2, because this negative sign is going this other side, right? 1 to 2 v dp minus d ke plus d actually it's going on dpe, right? And so for this case, the internal kinetic energy and potential energy is not changing, or it's negligible, so we can write w reversible equals to minus 1 to 2 v dp, right? So it will be kilojoule per kg. So this equation is 7.52. so here this negative sign, so for example this negative sign is representing that work done into the system, right? So for if we want to write, would like to, in the sign convention we saw that if a system consumed work, it will be negative, and if a system produced work, it will be positive. So for sign convention, we will write this equation for the steady flow system. If it is a compressor, for example, compressor consume work, right, whereas the turbine produces the work. So in general, if we write this equation, then w reversible equals to 1 to 2 v dp. So this is the equation for a reversible system, first of all, right? And that system is not closed system, it's a steady flow system. That means that system is continuously taking mass and continuously delivering or discharging that mass flow, right? So this is the work done by this type of system, steady flow system. So now some special case, let's consider for some special case, right? So case 1. So case 1 is saying that for the work input of the, for example, if it is a compressor and pump, those are work consuming device, then this equation will be w reversible, internally reversible, right? Or internally reversible, and work input equals to 1 to 2 v dp, and plus we can write the change in kinetic energy and change in potential energy, delta pe, right? So this is for compressor and pump. I'm not omitting this kinetic energy and potential energy, it's because of in compressor and the pump, they deliver or they discharge the liquid at different pressure and different elevation, right? So that's why there will be kinetic energy and potential energy. So this is the expression. Now if the case 2, right, case 2, if the fluid is incompressible, that means the volume is constant, it's not, volume is not changing. In that case, if the fluid is if the fluid is incompressible, that is, volume is constant, right? In that case, the reversible work equals to minus V times P2 minus P1, right? Minus delta KE minus delta PE. Actually, this minus, I'm just using this equation and this equation, right? And then just taking the integral. So B will be constant and it will come out from the integration. Then it will be only dp. If we take the integral of dp, finite integral of dp with the limiting factor 1 and 2, then the equation will be minus b of p2 minus p1, right? So that's the case for incompressible fluid. So if we, so this is all about the steady flow device, right? So if you have compressor, pump or turbine, then and it has the steady flow, then what is the work done? And also if you have like a compressible fluid and incompressible fluid, usually compressor and pump, they deal with the compressible fluid, but I mean, for example, if it is liquid, for in case of the pump, then what is the work done or work consumed by that device, right? So this is the case 2 is the representation of that scenario. So, and then another case, the case 3. Case 3 is the for a steady flow of a liquid through a device. For example, it could be pump, right? And that doesn't involve any work. So pump, it involves the work. However, if we choose the nozzle, right, if the flow through the nozzle, right, if the flow through the nozzle, then there is no work interaction, right? No work interaction. So in that case, the work term will be 0, right? So the right side will be 0. So if the right side is 0 of this equation, right here, if the right side of this equation is 0, then we'll get the V equals to P2 minus P1, and the kinetic energy, right, plus potential energy equals to 0. Now if we rearrange this equation, then we know that it will be P2 minus P1 plus V2 square minus V1 square divided by 2 plus mg Z2 minus Z1. So for this case, we know that this is the expression of the working fluid that is changing the pressure, changing the velocity, and changing the elevation, right? So if we have these three terms in an equation, then that equation we call it Bernoulli equation. Bernoulli's equation. I'm pretty sure everybody uses it in fluid mechanics classes. So this is the Bernoulli equation that has the three different terms. One is that it's called the head, right? Potential head, kinetic head, or the kinetic energy, and the work work done or work consumed by that particular device, right? So these three different cases for steady flow. Now we'll do a math problem, and we'll use one of the cases and determine that, if that one particular device, if it is a pump, then which formula we should use, and what would be the work consumed by the pump. If it is a turbine, then what for compressor or turbine, what formula, which cases we use, and what would be the work consumed or work produced by that device. We'll do it in the math problem. So let me work on the or let's go over the topic 7.11. That topic 7.11 is it's named minimizing the compressor work. Minimizing the compressor work. Minimizing the compressor work. So for we just derived that if compressor is in steady flow and it's in reversible, the process is internally reversible, then we know that work reversible work of that system equals to from 1 to 2 and v dp, right? We just found this equation and it was 7.56. So work minimizing of a compressor. How can we minimize the compressor work? So there are several ways to minimize the compressor work. Number one, making the process to an internally reversible. Making the process to an internally reversible by minimizing irreversibilities. Irreversibilities. For example, irreversibilities can occur due to the friction or turbulence, or non-equilibrium compression, non-quasi-equilibrium compression. So if we can make a compressor that doesn't have like a friction, or that doesn't have the turbulence within that turbulence of the working fluid, then we can reduce or minimize the irreversibilities. So if we can minimize the irreversibilities, then definitely we are also contributing in maximum minimum work consumption for that device. Another way to minimize the compressor work is reducing the compressor input or compressor work. So reduce the compressor work. So for working fluid of a compressor, we know that relationship between the specific volume and temperature is proportional. That means that if the temperature goes up, specific volume also tends to goes up. If we can reduce the temperature of the compressor, right, reduce the temperature of compressor, then we can reduce the volume, which ultimately, if we can reduce the volume of that working fluid, which ultimately reducing the work of from this relationship, if the V term goes down, that means W work will also go down. So that's how we can reduce the compressor, reduce the temperature of compressor will also reduce the SP volume, right? So these are the ways or methods that we can reduce the um, compressor work, because compressor is basically a work consuming device or energy consuming device. So imagine that if you have a refrigeration cycle or air conditioning cycle, and you are reducing or minimizing the work in compression cycle, that means that it will reduce your operational cost as well. So that's important, right? So let's go ahead and write some formulas that we may or may not use for you know for some thermodynamic process that involves within the work producing and work consuming device, right? So if we draw a PV diagram, right? um, and if we have this is state 1 and state 2, right? And then you have isentropic process, you have polytropic process, and you have isothermal process, right? So the first one is isentropic. This is polytropic, and this is isothermal. If you have this type of process involved in a thermodynamic system, then what is the relationship, or what is the relationship between the work and the working fluid properties, right? So for example, if the system is isentropic, right? If the system is isentropic, then work consumption of a compressor would be k times R times T2 minus T1 divided by k minus 1. So k is nothing but gas constant and universal gas constant R, and T2 minus T1 is the initial and final state of that temperature. So in terms of P, instead of like T, if we have the pressure in a compressor, it will change the pressure as well. So we can write this equation: compressor work input equals to KR T1 divided by k minus 1 P2 over P1 of k minus 1 divided by k minus 1. So this is for isentropic process, thermodynamic process. And if the thermodynamic process is polytropic, right, that involves some sort of heating, some sort of cooling, right? So there are a lot of refrigeration or air conditioning system that has intercooling of a compressor, or preheating of the compressor, or peak cooling of the compressor. So if like multiple system involved in the compression system, then it's a polytropic system, right? Polytropic system. So for polytropic system, we know that relationship between the PV equals to PV to the power n equals to constant, right? So in that case, the work consumption by a compressor equals to n times R of T2 minus T1 divided by n minus 1. If we write it in terms of pressure, then it will be n times R T1 divided by n minus 1 P2 divided by P1 to the power n minus 1 over n minus 1. And then last one is that if the system is isothermal, that means that compressor working in constant temperature, right? So isothermal condition, then the work consumed by that compressor equals to RT. Temperature is, this is a constant temperature, ln P2 over P1. So temperature is not changing, so in that case it will be RT ln P2 divided by P1. So that's the cases for, if, I mean, depending on the situation or depending on the condition of the compressor, you have to choose the work consumption. So from these three relationship, we can see that if the system is in isothermal condition, that has the, it will absorb, or it will take the less work input, right? That means if you can somehow constant keep the temperature constant of that compression system, it will have minimum work consumption or minimum work. So that's the relationship between the, thermodynamic processes and the work consumption by a device. And yeah, we just discussed about the work producing and work consumption for a device. So that's all about the topic 7.10 and 7.11. So I think that's all for this class, and we'll do some math problem based on these topics as well. Thank you.